Okay, thank you. Back to work, folks. All right. What I'd like to tell you about is some work that we've been doing on learning the foundations of knowledge, which, since we're talking about the future of machine intelligence here, I think is on the critical path. And I really enjoyed Matthew's talk earlier, and I hope that this juxtaposes in some interesting ways with that. But I want to start, I'm an old AI guy from way back. And so the function of AI, the goal of AI, to my mind, is to contribute to understanding the mind. And in particular, I think what we're actually good at is building mathematical and computational tools for modeling the mind. And that's done in service of both science and engineering. That is, we're looking at these cognitive phenomena, we're figuring out how to build computational models, and those computational models define a space of models, and sometimes they're used as hypotheses to get a better and deeper scientific understanding of the phenomenon of mind as it occurs in humans and animals. And sometimes it's used as an engineering tool in order to build better cognitive systems, and perhaps eventually cognitive systems that genuinely have minds of their own. And I believe that's actually a reachable goal. Now, once upon a time, the sort of founding enthusiasms that led to the field of artificial intelligence came out of symbolic representations and inference methods, what has been sometimes derisively called good old-fashioned AI. And there have been a lot of enthusiasm and a certain amount of disappointment because it turned out that that by itself wasn't enough to solve this immensely hard problem. And it became clear over time that we need a bunch of other methods, probability theory, statistics, control theory, dynamical systems. A lot of these things contribute in various ways to machine learning, but also to other aspects of understanding and modeling the mind. And it seems to be pretty clear that, again, contrary to some of our early expectations, we can't take the foundations of knowledge of space, actions, objects, and so forth, and simply program those up. They can't be programmed up by hand and then build a human-level intelligence capable of using that. Now, back in the early days, we actually thought this was going to happen. So one of the early triumphs was Terry Winograd's program Shrdlu. How many of you have heard of Shrdlu? Okay, that's probably a good solid half, 60% of the audience. That's pretty good. Shrdlu is an agent who has a single arm and lives on a tabletop of blocks. Now, for the philosophers there, Shrdlu was wrong. Shrdlu didn't have an arm, didn't have a tabletop of blocks. Shrdlu simply was a computer simulation. It was deceived. This is a perfect example of Descartes' demon who deceives you about what your physical world is. But deceived or not, it had perception. Now, this wasn't really solving a perception problem. It had direct knowledge of where the objects were and what their properties were. It had a really very sophisticated method for understanding natural language. It was able to do planning, and then it could act in its world. And although its world was in fact simulated, it actually took real actions in that simulated world, and it could observe the effects. And it could be surprised when things didn't work out the way it had expected. So this was amazing, and it convinced an awful lot of people that we were just right on the brink. Another 5 years, 10 maybe, we were going to solve this whole problem. Well, it didn't work out that way. So, and one of the reasons for that is that Shrdlu didn't have a lot of what I consider the crucial foundations for knowledge. So it talked about blocks and pyramids and boxes and so forth, but it didn't know what they were. Those are just symbols in its world. And so it has no real meaningful concept of objects, or for that matter, actions, or places or properties of things. So those are fundamental concepts that we, as people observing this, and that Terry Winograd, as the programmer, knew about. And those are grounded in our own perception and our own experience. But Sherdlu had never had those perceptions and experience, so they were not grounded concepts from Sherdlu's perspective. And the problem of actually doing that grounding hadn't even been formulated, much less people seriously trying to solve it. Now, there's other problems that came up in the AI world, and John Searle has been an enthusiastic critic of AI and came up with the Chinese room example. How many here are familiar with the Chinese room example? Okay, almost everybody. I'm not going to tell you about the Chinese room example. I'm going to tell you about the key idea underlying it. People can tell each other about it over coffee. But the key idea is behind John Searle's so-called refutation of AI is that an intelligent agent has meaning. The knowledge in your head refers to objects in the world. So it's important that there is meaning. Now, computation, pretty much by definition, is syntactic manipulation of symbol structures, which sort of by definition, again, is meaning-free. So symbol structures, when you get down to the guts of what reference is, reference refers to other objects that have already been created and that have been individuated, domains of things that are nicely behaved. So we have a situation where an intelligent agent has meaning, computation can't possibly have meaning, and so therefore the mind can't be explained by computation, QED, all done. Now, is this right? Well, Searle has convinced an awful lot of people of it. I think he's wrong. I think that there is some significant weight to this argument, and there are some important ideas in there, and I think those ideas are important for people working in AI. And they make a difference to how we structure an intelligent system. But does it refute the possibility of AI? No. Now, a lot of people have very enthusiastically tried to reply to Searle, and so here's my attempt. And this is based on a sort of constructivist view of developmental robotics. Part of the issue is that knowledge in a robot's head or in my head can't actually refer to objects in the world at all. That my head is locked in a box. It's connected to sensors and effectors through cables that send coded signals, and I'm not even given the code book for the signals. That's pretty much the Chinese room, right? An agent senses the world and acts within it, but does not have direct access to that external world. So what an agent does is to construct its own internal knowledge structures that are hypothesized explanations for the regularities in its experience. And so those internal knowledge structures are the thing that knowledge refers to. So reference sort of reaches out, but it can't get to the outside world. It just refers to the things that have been constructed. And we could go into much more length, but I want to talk about other things in this talk about that. Now, obviously, that's a pretty unconstrained picture, and you could say, well, in that case, you could have internal structures that do almost anything. You could be totally disconnected from the world. Well, what's going to happen if that happens? Well, Darwin is going to come and take you away. So, in order to function effectively in the world, those internal structures that get created had better correspond reasonably well to the world as it actually is. Otherwise, you're going to step off the curb in front of a bus, you're going to fall downstairs, lots of bad things are going to happen, and you're not going to be able to function. So, part of the goal of the AI researcher, to my mind, is to say, well, this is a very peculiar story. Can we actually make it work? So, appealing to yet other threads of history, one of the really compelling things is William James's observation about babies. So here is, he says, the baby, assailed by eyes, ears, nose, skin, and entrails at once, feels it all as one great blooming, buzzing confusion. Now I tell my students, nobody understands blooming, buzzing confusion like a roboticist. Because there you are, you're getting blooming, buzzing confusion coming in down the wire at many megabits per second, and you have to cope. So our problem is that what we're presented, and when I say our problem, I mean our problem as human agents having to grow up from babies and learn to function in the world, but also as AI researchers to try to build robots that can grow up and function in the world, is that what we're given is low-level sensory input and motor output, pixel-level experience. And what we need in order to function is high-level concepts, places, paths, objects, properties, actions, other minds, goals, purposes, so somehow we have to create a set of high-level concepts. I see this world as this room, not as a set of pixels and color patches, but as a set of chairs and desks and people sitting in it and camera and doors and so forth. Those are high-level abstractions that I can maintain even as I walk around and see them from a variety of different perspectives. So how do I get from here to here? So what I'm going to want to do is to pose this as a Gedanken experiment. I'm not going to say this is going to be exactly how humans got to be the way they are. I'm going to, among other things, sidestep the whole issue of innateness. And so the way I'm going to handle that is by saying, clearly evolution plays an important role, but evolution is a learning process. The species is learning certain things, arguably through breadth-first search. You send a whole bunch of organisms out there, some of them die, some of them come back and have children. So you learn certain things. Then the individual is born knowing certain things, and that individual then learns further things, which you might say is depth-first search. So let's just forget about all that and let's pretend that an individual is learning the whole thing, and that at the end of the day, we'll go and start saying things like, where are we going to draw the line between evolutionary learning and developmental learning? And that may be different for different species, as it obviously is. So here's the sequence that I want to use as a sort of broad brush research strategy outline for doing this. I'd like to say that my pretend agent, my learning agent, is going to wake up in the world with an enormous sense vector coming in, very high volume, but uninterpreted, so you have no idea what that information is. And you have a sort of moderate-sized motor vector, which goes out and makes things happen. And you live in a world of some structure, which you don't know. And it's your job to make a living before Darwin comes and takes you away. So this sounds unsolvable. And so that's why you get billions of years of evolution to get started. So what we're going to do is we're going to start by learning body space, the structure of the sensory input and motor output, and various control laws for achieving and maintaining certain feature values. Then we can start learning the local spatial model. What is the structure of local space as I move around in it? And can I look at statics and dynamics? Looking at that, I can start abstracting objects and the actions that affect them. Hopefully, at certain points, learning properties and affordances and how to use things as tools. From there, I should be able to learn about goals, beliefs, and plans, and eventually to learn about other agents, which might lead me to communication. Now, if you've been watching my progress from the past tense to the future hypothetical, you can probably infer that where we are right now is right about here in this list. And so I'm going to show you some examples of that. But first, I want to show you some of the previous work that helped me get here. So we'd done some work a long time ago, over a fairly long period of time, and it's still continuing as one thread, on cognitive mapping. How an agent can explore a large-scale environment like a building or a city and build a cognitive map of that environment. And one of the things that we learned in the course of that was that certain kinds of high-level concepts, in particular places, can be abstracted from this low pixel-level experience simply by looking at the behavior of the control laws. And that abstraction was the key to being able to build a cognitive map with very, very weak assumptions. And so this was sort of the paradigm that we followed in order to do a bunch of later work. So a key idea here is the notion of a distinctive state. Now, I can have pixel-level experience and still execute a control law, for example, to move along here, keeping a constant distance from this set of stuff. And if I form a control law, and then I get into a particular neighborhood where something has changed, there's a barrier here, then I can switch so that I'm following a hill climbing control law, for example, to get to the point that's equidistant from these two places. Now what that means is, let's suppose I'm coming along, I get into this neighborhood where I can do my hill climbing. The peak of that hill climbing process is the fixed point of that control law, and that's the distinctive state that ends up representing this neighborhood. So now if I want to go back to some other place, I follow a control law. There's always errors in motion. So we're going to accumulate a certain amount of error, and maybe this is where I'm trying to get to, but I get somewhere else, but it's within the basin of attraction. And I can say, how do I get to that distinctive state? I do the hill climbing, get to the distinctive state. I can do that same thing forward and backwards, and that enables me to abstract this fairly complex pattern of behavior to a very, very simple abstraction. I have 2 points, and I have a reliable motion that takes me from one to the other, eliminating cumulative error on the way. And so it's an example of going from pixel-level behavior to higher-level concepts. And so in exploring an environment like this is a simulated environment. Here we get the control laws. Here we get the distinctive states that it finds. It travels through this environment, finding various distinctive states, occasionally checking out hypotheses, and so forth. And in the course of that, it ends up being able to build a much, much simpler, much smaller finite graph to represent that continuous infinite environment. So this is actually pretty useful. Now I want to carry this on to a somewhat more complex robot. So this robot is called Lassie, and it's a mobile robot, moves around the world. It's got a laser rangefinder on the top. A laser rangefinder sends out 180 rays over 180 degrees and measures the distance to obstacles. And it perceives the world in a plane that's probably about 12 or 13 inches above the ground. So it lives in a two-dimensional world, moves around in this two-dimensional world, and this is what a particular laser image looks like at one point in time. So here is our agent. So the agent's motor vector is what can get it to move and turn. Its sense vector is the laser rangefinder. We've done some other experiments to to use more sensory modalities, but here I'm going to look at just this one for now. And now what I'm going to do is I'm going to take you through a series of movies showing very briefly what it looks like to the agent to perceive the world through this sense vector, and how it, how it gradually builds higher and higher level structures on top of those the original low level structure. And I'm not even going to start with this. I'm going to start with a completely disorganized, randomly ordered sense vector. So assuming that you don't even know the order of the pixels, and all you have is a vector of real valued numbers. So here you are, something is happening here, and you don't know what it is. So how can you deal with this? You are cooked, right? Well, you better learn something, because you know what's at stake. Well, if you have no other information, what you can do is you can correlate things. So let's go and correlate. This is a 180 element vector, time varying. Let's correlate each of the pixels, each of the pixel values with each of the other pixel values. Well, it turns out that thanks to the almost everywhere continuous structure of the world, there's enough information in there so that you can say nearby pixels in this array are going to be highly correlated. And so high correlations, we're going to treat high correlations as implying that they're close together. And thanks to that, we can actually put the sensor array into the right order. And so as you can see, this makes a great deal more sense. It still doesn't make sense, but we're obviously not in quite as bad a situation as we were in before. Now it turns out that using this set of pairwise correlations, we can do more than just infer the adjacency. We can actually infer the fact that these are in a semicircle. And I'm going to show you just a tiny bit of the mathematics behind that after this next slide. But what we can do is actually infer this as what's happening. Now you can see this is actually a great deal more sensible. It's easier to see when it's holding still. Right now the changes are conflating the egocentric motion of the robot as it moves and the dynamics in the environment. But what we've got here is an egocentric range image. Now we actually do those first two steps in one go. So how are we actually going to do that? Well, what we've got initially is a completely disorganized bag of pixel values. And so we've got a set of sensors. Sensor I is one particular pixel, and we've got its value for values of t from 1 to n. So what I'm going to do is I'm not actually going to do the sort of Pearson's correlation. I'm going to take the value of sensor I at time t and compare it to sensor j at time t and take the average. And that's going to be my distance between sensor I and sensor j. Take the average over all the time. Now this turns out to be essentially something called L1 distance by people who care about that sort of thing. Euclidean distance is called L2, and there's a related method that came up sometime later called isomap that uses that. There's another guy in Scandinavia, no, Hertfordshire, I think, uses mutual information. And a former student of mine has done something similar using Gaussian processes. Now, I don't have any particular stake on which of those distance measures you use. I just want to have some set of distance measures that you can compute without prior knowledge. So now, given those distances, I can take the sensors, the pixels, and put them into a high-dimensional space. So if I have 180 range sensors, I can put them into 179-dimensional space, reflecting those distances. And then I'm going to use principal component analysis to find the dominant eigenvectors, the ones with the largest eigenvalues. Now, here was a previous example with a simulated robot that had 24 sensors, and one of them was broken. So it actually filtered out the broken one, took that set of distance measures. Here are the eigenvalues, and you can see that the first two are pretty big, and the rest of them are really small. So almost all the juice in this distribution is in these first two dimensions. So in my high-dimensional space, the positions of those sensor pixels can be thought of as laying on a really thin pancake. And we can use the eigenvectors to define the dimensions of that pancake. And so we project the pixels, the pixel positions, onto that two-dimensional space, and we get this. Now, in fact, then what we do is we say, well, maybe there's a little more information in the leftovers, and so we relax those positions using the full information in the distance metric. And as you can see here, we get no significant change. But what we've done then is we've gone from this and determined that these pixels are in a particular orientation. Now, with the laser rangefinder array, this is what we get. So we actually get this semicircular structure of these pixels. We decided to try it just to see whether this generalized. So we tried it with a very, very simple retina called the roving eye. So we have this 5 by 5 set of photosensors, and it moves in X, Y, and theta over this picture that my student took on vacation one day. And so it gathers a bunch of values. We do the same operation, and what we get is this set of eigenvalues. So here it's still clear that two dimensions captures most of what's going on, but there's a lot more juice left in the higher dimensions. And so if we simply project those positions into two-dimensional space, we get this set of positions. But then if we take this as an initial state and then we relax according to the entire distance measure, we get what is actually the correct organization of the pixels, up to rotation and reflection, which of course doesn't matter at all. So that is an explanation for how we end up with this particular model or interpretation of what the sense vector is giving us. But this is still pretty frustrating. Now, if we look at various segments of this, now it's holding still for a while here, but what we'll see is that these things move in a largely continuous way. And so the next step here is to say, how do we preserve as much invariance as we can? So what we're going to do is say, let's take the first frame, and we're going to declare this frame of reference is going to be our canonical frame. And then we're going to take the second frame. And now what I'm going to do is I'm going to move the frame. I'm going to translate and rotate a little bit to maximize the match between the first frame and the second frame. And then I'm going to do the same thing with the third frame, shifting and rotating a little bit in order to maximize the match. So I take my whole sequence of observations and put them into the frame of reference of the first frame. Now what that effectively does is gives us a world-centered frame of reference. So what we're doing is we're going from egocentric to allocentric space here by taking the portions of the space that are invariant that we can actually map from one frame to the other and matching them. Now, as a result, the origin of the egocentric frame moves around. It moves in position and orientation. And so we've actually created a new object in our knowledge representation, which is the trajectory of the origin of the egocentric frame, which is actually the position of the robot. Now, as you've noticed from here, the robot never, ever senses itself. So there's no pixel value that corresponds to the robot. On the other hand, this process of matching has created a symbolic object that stands for the robot itself. Now, there's much more to be said about that. Now, when we put together this visual representation, we were using the laser rangefinders, and we were using a little red dot to stand for the endpoint, and we connected that with a blue ray to the origin, and that made a nice attractive picture. But the blue rays are getting distracting. So this is the same thing, but without the blue rays. And as you can see, there's some more information in here. And so thanks to the power of your visual system, you can see a heck of a lot more structure here, which our algorithms are going to have to try to capture. Now this has still, for all of its benefits, it's still pretty frustrating. And part of the frustration is that it's so much in the instant. And what we want to do is to collect information over time. But we've got an allocentric frame of reference. We can create a high-resolution histogram along each dimension, take the cross product of those to give a grid, and what we end up with is essentially an occupancy grid where we can put information here and collect data over time so that we've got parts of the map that aren't currently in the field of view, which is red. This is the egocentric origin. And so we collect a model of the environment. So we're starting to build a model of the actual static environment out there. Now what we've done is we've started with uninterpreted sensors and effectors, and we've used a set of statistical learning methods. And as a matter of research strategy, what we've decided to do is to use methods that are, we're not putting a priori constraints on which statistical learning methods that we use. Anything that doesn't have explicit domain assumptions about it. And then at the end of the day, we'll go back and minimize over the set of tools to try to get a minimal set of tools. But our goal was to learn objects. And we haven't got objects yet. We've actually still just got pixels. We've just got better pixels. We've changed representations and frames of reference, but we've still just got pixels. So what we want to do here, what we are in effect doing at that last stage is we are taking the sensor stream. This is the sensor stream, the sense vector as a function of time, and we're explaining it in terms of the static model, that is that map that we're building, and the pose of the robot, the pose of the viewer, that is the location of the origin of the egocentric frame. And then this is just a projection function that says, given those things, what do I predict this is going to be? Now that model is not going to be perfect, and so these are the discrepancies between the model and the actual sense vector. And so now it turns out that this is basically a static world model. And the dynamics of the people and objects that are moving in that world are noise, and they just have to get averaged away. And so what we have to do is to cluster those noise pixels, track them over time, and merge those images to make shape models, and then eventually we're going to learn actions on them. And this was done in collaboration with my student. So now what we're going to see, the green pixels are just the discrepancies between the static world model, which is this black thing, and the sense elements. So now we're going to take those discrepancies and we're going to cluster them. The reason these are flickering in color is to show that they're clustering independently at each time frame. And here is our egocentric origin, which is the location of the robot. Once we've got them clustered, we can track the clusters over time. Now this thing doesn't have object permanence. So as you'll see, some of these objects go for a while and then they vanish because the tracker loses track of them. This one is going to persist. And so at the end of this process, what we've done, again, starting with uninterpreted sensors and effectors, is we have learned a model of the static world, a representation for the robot's own pose. We've learned about this object that was in a fixed position. We've observed an object following a trajectory through the world. And so we've built a very rich, higher level model of this world. Now these are individual objects. One of the things that we can do is actually combine the individual views of those objects in order to build models of the sort of shape models of the objects. I'm not going to pursue that very far. However, part of what our goal was to go from objects to actions. So how are we going to learn actions? So we've got a bunch of object attributes like position, orientation, and shape, and we've got these both in the egocentric and the world-centered frames. So what we're going to do is we're going to do motor babbling because we don't know how to do anything else. That is random actions. And we're going to observe and record any attribute changes. And then we're going to cluster that data. And we're going to find situations where we get a cluster of qualitative changes of attributes, like places where something increases or decreases. The effect, are there clustered prerequisites for that and associated motor signals. Now what this effectively does is lets us learn very simple models of actions. Now these are actually a lot like strips models of actions, where an action is modeled as a prerequisite, a motor, and an effect. And the motor commands here are very, very simple. Now for this mobile robot in this environment, there really isn't very much it can do. It doesn't have hands. So the main things that it can do is it can turn to face a desired direction. It can move to get to a desired place, and it can push an object. So it's only allowed to play with light objects like trash cans and cardboard boxes. And so it can push things. So then we wanted to demonstrate this. So what we did was we said, we're going to give it a goal location for a particular object in the world. You're going to push this trash can to that place. And we gave it a very simple backchaining planner that says, if you want to make something happen and you have an action that can make it happen, do that action. If you don't have the prerequisites for that action, figure out some way to get the prerequisites true. Now, I would have loved to learn the planner, but I had to have mercy on the poor aching graduate student because he had been in school for a number of years. So here is that scenario. So here's Lassie, there's the recycle bin, and here is the spot that that's supposed to go to. And those correspond to these places. Now, notice that Lassie has learned how to do the space, what the objects are and what the actions are. And then it goes and it makes a plan for getting there, which is to say it has to push this to that location. In order to push it, it has to get to this place and get into the right orientation. And in order to get there, it has to turn and travel from here. So we're going to watch that happen simultaneously on the two sides here. So here he turns over there, he's heading up here, and he has to get to the right place. And now he's going to push, come on, come on. not all that smart. So then he pushes and misses. So he's got to go around to the other side and nudges it into place. Woohoo! Yeah! You know, you talk about getting 150 miles through the Nevada desert, that's nothing. That's nothing. This is the real thing. So notice, this is what I would claim is a constructivist agent. So this guy has constructed his own model of itself in its world. His sensors and motor controls, these different spatial frames, object shapes, localization. These are self-created abstractions. These are not knowledge of the world provided by an external authority. Now, I'm going to have to qualify this a little bit in a minute. Now, and again, because they correspond pretty well with the actual structure of the world, they actually guide effective action. Now, here's the qualification, that we're using a lot of different learning methods. And the application of these has actually been manually scripted. I mean, we knew the intermediate states, and we said, okay, this is what you're going to do to learn this. This is what you're going to do to learn this. Now, we believe that this can all be done autonomously. One way to do it is to say, let's just have all these methods running in parallel. And that some of them are just going to spin their wheels because there's nothing useful for it to work on, and it's not going to produce anything useful. Other ones are going to produce something effective, and so the preconditions and the results are going to give that sequence. Another possibility is the method that Jürgen Schmidhuber was talking about, which has been called, actually by someone else, intelligent adaptive curiosity, which is to reward improvements in predictive accuracy and search for the places where you can gain these improvements. So the effect of this is to really seek the frontier of knowledge and avoid things that are either useless where there's nothing to be learned, where there's nothing that you're able to learn yet, or the boring things that you already know. Now, we're trying now to move on from 2 dimensions to 3 dimensions. And so one line of work is to say, let's take visual input and start to learn to recognize objects in streams of visual observations with my student Shanghai Shu. And we're also trying to learn a better hierarchy of actions, in this case with a simulated robot with a simple arm and objects in the world. And both of those are making progress that we're happy with. One conjecture here is that this, which we sometimes call bootstrap learning, is really going to work wonderfully for all kinds of sufficiently rich environments. The other question, as I mentioned earlier, is we'd like to be able to figure out what the minimal set of statistical tools will be that'll support this. And related to that is the question of how we would want to divide this up between evolutionary time and developmental time. Now, as an example here about deeper learning about objects and actions, I just want to show you this young man, 8 months old. And watch how systematically this child is learning to do things. 1, 1, 1, 2, 3. A few of those. Suck on it for a while. Bang. Now watch this. Watch this. Huh. I've got a whole smash of these videos, and these are this is fantastic. I mean, you can sit on the edge of your seat watching this kid deliberately explore these capabilities. It's just unbelievable. Any roboticist would give their left arm if they could have their robot's right arm do that stuff. So now I wanted to just close with a couple of brief remarks on the future of machine intelligence here. I claim that this kind of developmental learning of foundational knowledge is on the critical path, and may be the critical path, to human-level machine intelligence. And that if we can figure out how to do this stuff, then we may be able to build AIs that can actually achieve intelligence that belongs to them. And so I think it's quite clear that the world is way too complex for foundational knowledge to be programmed in by hand. Now, this requires interaction with the physical world, or with a world. Does it have to be the physical world? Well, it sure helps us that it's the physical world. The sort of mesoscale physical world that we live in is almost everywhere continuous, and that has nice properties that are actually important for the learning algorithms. And what if you have an AI that's trying to learn these things and it's grounded in a very different world? Now, the internet is basically discrete, not continuous. You can find little continuous world simulators in there, but lots of things happen discretely in big jumps. And so is it as learnable? My conjecture is no, but who knows? The other thing is this intelligence explosion concern is a real concern, but it depends on being able to do this learning in a world that's operating on a timescale of microseconds rather than on a timescale of seconds like we do. Now, what is the physics of the world at a timescale of microseconds? Now, it's very, very different from the timescale of seconds. Does it have these learnable properties? I don't know. I'm concerned. I mean, if I drop this thing, which I'm not going to, but if I drop it, it's going to take less than half a second to hit the floor. If I were operating at 6 orders of magnitude faster speed, it takes about 2 subjective weeks to hit the floor. Paying attention to that phenomenon and learning from it would be a real challenge, especially for a baby. So I think one hypothesis to be considered is that an intelligence explosion may be impossible due to the physics and timescale that's necessary for a world to be learnable. If you have to interact with this mesoscale world, you're not going to achieve superintelligence in a few minutes. Now, this will be an interesting topic to discuss, and this is certainly not a definitive argument by any means. And here's a whole mess of articles. You should read them all. But thank you very much.